Hello everyone, welcome to Modern Semiconductor Devices for Integrated Circuits lecture number 8. So far, uh, in this module, we have completed evolution and uniqueness of semiconductor technology, the concept of equilibrium carrier concentration, minority and majority carrier concentration, the concept of thermal equilibrium, quasi-equilibrium, wave particle duality, the difference between intrinsic and extrinsic semiconductor plus the numericals, then the energy band diagram for intrinsic semiconductor, energy band diagram for extrinsic semiconductor, and we have seen the various carrier transports, drift and diffusion process. Then last time we have seen the injection level concept, right? So today also we have seen, you know, what do you mean by excess carriers? Next time we'll also see today how does the excess carriers are generated. Excess carriers means over and about equilibrium. Okay, and with the process of high level injection and low level injection, excess carriers will be created. All right. So let's begin today. Write down effect of the first concept which we are going to discuss today is effect of excess carriers on energy band diagram. Short form I'm writing EBD. Acha, quickly tell me the formulas. Let's recap the formulas. Do you recap? NO is equal to NC exponential of minus of EC minus EF upon KT. And what is PO? NV. You know what is NC and NV? Effective density of states for conduction band and valence band. So EV minus of exponential of EF is Fermi level, Fermi energy level. Okay, EC and EV are valence energy level, conduction energy level. What is P naught and N naught? Majority carrier concentration. If it is N type, it is P type. Also, you can write it as, how can you write this as? NNO, correct? And this can be written as, because these are majority carrier concentration. And minority carrier, how will you determine? PNO, Ni square upon, correct. Here, NPO, it will be Ni square upon, got it? Then, this will characterize NO and PO with respect to same Fermi level, EF. Okay. Now we can write NO or PO with respect to intrinsic carrier concentration and intrinsic Fermi level. So it will be NO will be equal to Ni. Remember we have written this formula also. Exponential of EF minus EI. What is EI? Intrinsic Fermi level upon KT. PO is again Ni. Ni and Pi are almost same. Ni exponential of, because for intrinsic semiconductor number of electrons and holes are same. So Ni is equal to Pi. It will be EF minus EI minus EF upon KT. What is KT? Thermal energy. I hope you all know that. So please write this down. Where EF is Fermi level. What is EI? Fermi energy level actually. What we intrinsic Fermi level. Let's say for example, if we want to write it quickly please. Let's say for example, we have to draw the energy band diagram of M type silicon. Completed. This is the revision which I am doing. Even if you don't write the formulas, it's fine. But we are going to compare with the excess carriers. That's why. It's fine. Now just wait. Let me draw the energy band diagram. Then you can complete this. Okay, just wait down. Hold on. So let's recap energy band diagram for N-type semiconductor. So we have conduction level. This is conduction band, energy band, valence band. What will come at the center? Intrinsic Fermi level. So that is EI. Where will the EF come? Where will be a donor level also? No? Donor level is very, very close. Now we'll not draw the donor level because where it is exactly, can you tell me? Once for the last time we are drawing it, it is very, very close to conduction, almost. Because how much energy is required for any free electron from donor level to go to the conduction band? So this is donor level for the last time I'm drawing it. Assumed we have the donor level present. Now where is the Fermi level? Near to, yes, here. I hope you know all the. This is EF. If you want to write for n type, it's understood it's Fermi level, but EFN and EFP. EFN and EFP, when will you write? When you have both type of impurities. So right now your EF is there. Okay, this you already know, but if you want to draw just a recap, now complete it. Okay, can I go to the next slide? Yeah. Can I go to the next topic? This we have already written. This is just a revision. So you can carry it out. I mean, write it down later also. This is revising it because we are going to modify this. So next is write down the effect of excess carriers on energy band diagram. The effect of excess carriers on the energy band diagram is the formation of different quasi Fermi levels. Quasi Fermi levels for electrons and holes. The effect of excess carriers on the energy band diagram is formation of different quasi Fermi levels for the electrons and holes. Okay. Let me draw and show it to you first. Then I'll explain. So let's draw this energy band diagram. Write down. Topic is quasi Fermi level. Bracket under. You know what is LLI, right? Low level injection, and HLI, high level injection. So let's draw the energy band diagram for N-type semiconductor under low level injection. Where low level injection delta is how much? Around 10 raised to 12. Okay. ND. What is ND? Donor concentration, carrier concentration, that is around 10 raised to 15. So this is majority carrier concentration. NNO. PNO will be this divided by Ni square divided by this. Okay. Now the normal will be same. The conduction band and valence band will start with conduction band and valence band. So here we have conduction band. Up till here it's same. Then we have valence band, and at the center what we have? Yes, intrinsic Fermi level. Donor level and all we are not drawing right now. So what is happening is here, everyone concentrate, stop drawing. So now there was one Fermi level earlier, what where we would have drawn that near to conduction band. Now due to this low level injection, there will be two Fermi levels. The Fermi level, write down over here, the Fermi level splits into two quasi Fermi levels, which is EFN and EFP. What is EFN stands for? Is the quasi Fermi level for electrons, and EFP is quasi Fermi level for holes. Are but you will say, sir, N-type semiconductor, where does the hole comes? See, low level injection will affect what? Minority charge carrier. So minority charge carrier concentration will increase. Earlier, how much it was? I think Ni square is 10 raised to 20 divided by 10 raised to 15. So that around 10 raised to 5. Now we have added the injection 10 raised to 12 only. So when we add 10 raised to 5, 10 raised to 12, it becomes a significant number. So that should be represented over here. Yes or no? So that will be this. So so your Fermi level EF splits up into two quasi Fermi levels, EFN and EFP. So one quasi Fermi level is over here near to the, this is, listen, first draw EFN. Okay, another quasi Fermi level is over here, which is EFP. Okay, now I'll tell you really interesting thing. You know where is this 10 raised to 15? You have written a 10 raised to 15. This is basically what? Majority cardiac concentration NNO. Yes or no? So this is this distance. You remember in the formula it is NO is equal to what? What is the formula? NC EC minus EF. So this is that EC minus EF. Here, this one, this NO. EF minus EI. So this is that EF minus EI. Okay. Now this concentration is NNO. It represents 10 raised to 15 per centimeter cube. Understanding the distance between these two energy level? Can you tell me what does this represent? The lower one. This represents how much concentration? Because now PNO becomes what? Equal to delta. So this concentration is this much. Okay, draw it. And what is the concentration over here? Concentration here is Ni. Yes. So this is the energy band diagram for a N-type semiconductor under low level injection. So we can ask you a question. Draw the energy band diagram for a phosphor doped silicon with a concentration of 10 raised to 15. This is a question. Under low level injection of 10 raised to 12. So you have to draw this. Alright. Okay. Written. Now, completed this? Okay, completed, no problem. Did you understand why is EF minus EI will be representing NNO or NO? And why is EI minus EFP is representing minority carriers? Why this is 10 raised to 12? Because of low level injection. If there was no low level injection, what would have been this number? 10 raised to 5. Ni square divided by 10 raised to 15. That will be 10 raised to 5. So due to low level injection, minority carrier concentration is disturbed. Okay, now let's get back to these formulas and not make you write again. What is the effect of excess carriers? We have different energy levels for electrons and holes. So what will happen over here? What will happen over here? Here we can write EFN and here we can write EFP. Understood? Only that much difference is there. That's it. Here we will write EFN and here we'll write EFP. Okay. Here the carrier concentration N will be greater than N naught. N naught is equilibrium carrier, na? And here P will be greater than P naught. Is concentration of electrons and holes. So these are the modified equations for effect of excess carriers. EF becomes EFN and EFP. Now quasi Fermi level are realistic in nature. Intrinsic Fermi level are hypothetical. So quasi Fermi level are the ones which are used for non-equilibrium conditions. And actually in reality the current flow is in non-equilibrium conditions only. And how we do the analysis? We do the analysis from small deviation from equilibrium, which is quasi equilibrium. Now the real question is, this you have understood now how to draw it. How will the same energy band diagram look like under high level injection? So let's write down. Let me give you a question only. Draw. So that will be easier for you all to study. Now draw energy band diagram for a phosphorus doped silicon with 10 raised to 15 per centimeter cube concentration. High level injection is imposed with delta equal to 10 raised to 17. What do you mean by phosphor doped silicon? N type, correct. Now, any predictions? Acha, first let us draw the conduction and the valence band. So this is my conduction energy level. This is my valence energy level. EI will come at the center, right? Okay. Now what? This we are drawing for N-type silicon under high level injection for delta equal to 10 raised to 17. So write down here one note. Under high level injection, excess carriers. What do you mean by excess carriers or excess holes and electrons? Excess carriers means over and about equilibrium because of high and low. Excess electron and hole concentration will be same. I'll give you an example. Listen, high level injection is, listen example, for example, high level injection is 1 crore or 50 lakhs, let's say. High level injection is 50 lakh. ND is 10 lakh. Minority carrier concentration is 50,000. Now, if you impose high level injection, if you add for 50,000, 50 lakh, 50,000 will be negligible. So low level concentration, I mean, your minority carrier concentration will become 50 lakh. What happens to majority? Majority 10 lakh tha. Now, if we added 50 lakh, I mean, it will definitely get disturbed. So what happens is under high level injection, the excess electrons and hole concentration will be same. Understood? So how will you show the energy band diagram? There will be both EFN and EFP. Since the concentration is very, very high. Dekho, the higher the concentration, the more near the Fermi level is to the conduction or the valence band. Away. Okay. So where will you draw it? Here it is. And they will be equidistant. So this distance and this distance is same. Are you getting it? EFN, EFP. Are you understanding? You know what? What does distance mean? nahin, how much it is? Both are 10 raised to 17. Correct? I told you, na, given an example. 1 crore. I'm 50 lakh. I've given the example. So we add it to 50,000 or let's say 1 lakh. It will become that only 50 lakh only, right? Both are same. So this is an example of a high level injection. Okay, completed. Completed this topic. Everyone, next write down next concept, mechanisms of generation, recombination process. Mechanisms of generation and recombination process. Yup, everyone. So you have draw the energy band diagram. The first which you are showing is direct G slash R. G stands for generation, R stands for recombination. Acha, in which case excess carriers are created? Generation or recombination? Generation. Thermal generation process you understood? What it is thermal generation I've explained earlier, na? What was it? Valence band to conduction band. It's a generation process, thermal generation. And how much energy is required for that? Energy band gap energy. So if you have a carrier over here, and if it reaches over year to year, that process is called as generation process. And what is recombination? Opposite, the reverse. This is recombination. This direct recombination, I mean, I'll show you some today picture today. This is called as direct recombination and direct generation process. This is for gallium arsenide. This is not for silicon. This is for compound semiconductors. So whenever an electron meets a hole, there will be a recombination happening. Or whenever an electron or a hole gets energy, you know, band gap energy, it will generate excess electron and a hole pair. Electron hole pair is generated. I guess you have made you right now. Ionization process and thermal generation. Ionization either electron or hole, but thermal generation electron hole pair is generated. So that is generation process. In case of a direct band gap semiconductor, there is a concept of direct band gap and indirect band gap, which we are going to discuss now. So directly, without any restriction, the carriers move from one energy level to another energy level without any restriction. Okay, fine. But there is another process, which is this. See, what is this? These are all energy levels, right? You're in a crystal lattice. You know what is a crystal lattice, right? Like this. Behind also. Are you following? So all the silicon atoms are arranged in tetrahedron form, like this. You must have seen, and neighboring ones also. So this crystal may have defects, impurities. What do you think? How many charged particles are present? Do you know electrons and holes? There are photons also. There are phonons also. What are phonons? Vibrating silicon atoms. Those are also present. There will be some other type of impurities also present. So whenever the carriers, the charge carrier, so there will be something called as, see, these are levels. Let's say if you want to jump from first floor to second, I mean, you want to go from, you want to jump from second floor to the first floor directly. But in between, if you have some compartment or something to land on, so where it will be, the jump will be easier. Direct second floor to first floor without any restriction in between, or there is some restriction in between and then you flow. So is it easier to flow from year to year, or there will be some, let's say there is some defect level. Here I'm drawing defect levels here. Impurity level, there will be impurities. So you can stop over here and then go over here. Okay, so these levels are called as defect level or impurity level. These are present for indirect bandgap semiconductors or impurity level. So what happens is any same process of generation will now happen this way. So first it will jump to the impurity level. Just imagine an impurity site, and from here it will go up. Are you understanding? For silicons, this is what happens. And what about the, this is generation process. What about the recombination? Same thing. This is recombination process. All right, and this is true for indirect. This is called as indirect. Why indirect? Are you understanding now? Via defect level. So this is indirect generation recombination, and this happens in elemental semiconductors, which is silicon. So within the energy band gap, see which is the energy band gap? This is the energy, na? EC minus EV. See, EC minus EV is how much? Anyone can tell me for silicon? This is for silicon. So within the energy band gap, there will be impurity level. So these carriers will stay at impurity level, and that impurity level is not the way throughout. It will be like small levels. There will be many levels over here. So um, in silicon, the recombination occurs in the impurity sites. These are called as impurity level or impurity sites within the energy band gap. So near a certain defect or an impurity level within a semiconductor, if an electron and a hole meet, recombination will occur. Now, now I'll show you the difference between direct. Let's discuss the difference between direct and indirect bandgap semiconductors. Now you understood now direct. I mean, little bit of concept of direct and indirect generation and recombination. Now we'll understand what do you mean by direct and indirect bandgap semiconductors. Completed this much? Write down the another concept. Direct versus indirect bandgap semiconductors. So what I'm doing is I am plotting slightly different. I'm plotting momentum, crystal momentum versus energy levels. This is crystal momentum. So these levels, see how they look like in case of direct semiconductor. See like this. Okay, this is conduction band. This is valence band. Sorry, let me write it this way. This is conduction band and this is valence band. You know what we draw? We draw it like this, na? This is what we draw is this way. We call this as EC. I told you na the carriers present at the bottom edge of the conduction band and top edge of the valence band are available for conduction. There will be carriers here also, but mostly the carriers which are over here at the bottom edge of the conduction band and top edge of the valence band, they are available for conduction mostly readily. This is EV, and the difference between them is EG in general. 1.1 nahi. For gallium arsenide it's not 1.1. So if a recombination is about to happen, can it happen directly over here without the loss of momentum? You know what is a momentum, right? Or cycle traveling at let's say 20 kilometer per hour. If it hits you, I mean, you will fell down, but no severe injury will happen. If a train traveling at 20 kilometer, because of its momentum, if it hits you, you might fell down and even fatal injury will happen. Understood? The momentum of the cycle is not that much. I mean, you are more stronger than the cycle, so your body will take the impact. Yes or no? But whereas a train, the momentum is so high that you will fell down even at 10 kilometer per hour. All right. So this is direct band gap. Without loss of momentum, directly the carriers from the conduction band can, whenever they meet the holes in the valence band, the recombination process happens. So this is recombination process. This is direct band gap semiconductor. And what is the example of a direct band gap semiconductor? To your surprise, silicon is not a direct band gap. This is gallium arsenide. What is gallium group in periodic table? Group 3. Arsenic, group 5. So group 3 and 5 elements are combining together to make gallium arsenide. So here the momentum change is zero. Yes or no? Here the momentum change, let's write that down. Observation. Here the momentum change is zero. For the transition. So since there is no momentum change, momentum change, photon can be given away very easily. Whenever electron and a hole meet, they give away a photon. So that's why gallium direct bandgap semiconductor are used for light devices. Yes, where it emits light. So these are suitable for, write down, optoelectronic devices. Suited for optoelectronic devices. You know there are different colors of light. What does it mean? Different wavelength. You saw na wavelength lambda. Ah, you can use it. LED is actually three elements: gallium, indium phosphide. So it's made up of three compounds and of different ratios. Since gallium arsenide I'm writing, so it can be Ga zero point 0.5, or sorry, Ga can be 0.2%, arsenic can be 0.8. I mean, there's some more details about it, but just generally we write it as this only. Okay, this is suited for optoelectronic devices used for making LEDs also. I mean, direct band gap. One example is gallium arsenide. Another example can be more compound semiconductors together. Understood? Silicon, for your information, it's not suitable for optoelectronic devices. No LED is made up of silicon. Okay, let's see why. So draw this diagram. Next, momentum versus energies. See this realistic picture. Huh? I mean, now where is my conduction band? This is my conduction band. Where is my valence band? EC, EV. Now if a recombination have to happen, how it will happen? From here only na carriers are there. This is my conduction band. This is my valence band. How it will happen? This is recombination, right? Is there a shift in momentum while the carriers are recombining? Is there a shift in momentum? Yes. How much is the shift in momentum? Delta P. And there are, I just showed you above, indirect recombination and generation happens, right? So possibility of emission of a photon is very less because there are defect levels. So here, this is an example of, are you understanding? So here, while the carriers are getting recombined or generated, what will happen? There is a shift in the momentum. So it's one carrier in the conduction band is with different momentum. One carrier in the valence band is with different momentum. Just an example I've given you of a bike and a train. Same traveling at 20 kilometers, but their impact is different, right? So that is, these are called as indirect band gap. Indirect meaning our understanding, right? Direct transition without a loss in momentum is direct band gap. What is indirect band gap? With a significant change in momentum, if the carriers are traveling, then there is an indirect band gap. No, no, no. That is not different. That is different. Here there can be defect levels also. So here it can be a via transition from year to year, from year to year. Indirect band gap. Yes, exactly. Yes, yes, exactly. That's why it's easier to emit photon. So your example is silicon or germanium. So here during the transition, that is electron from conduction band to valence band, there will be a change in momentum. Therefore, we cannot use silicon for optoelectronic devices. Understood this? Now, one more concept I'll discuss today, then we'll rest for today. We are one more session away from completing this module. Completed this? Next, write down Einstein relation. Einstein relation is diffusivity. This is related to diffusion and drift process. Huh? What is diffusion process? And drift process? Potential gradient. Diffusivity is equal to mobility into thermal voltage. So D is equal to, mobility is represented by this symbol mu. See, like this. And thermal voltage is represented by KT, right? It's normally call it as VT. It's KT. This. So we are writing VT over here. So this is very, very important Einstein relation. And this holds under quasi-equilibrium process. Acha, what is VT given by KT by Q? Huh? Because KT alone is energy, na? KT by Q will be voltage. VT is given by KT by Q. And how much is VT at room temperature? 26 millivolt at room temperature, 27 degrees Celsius. You can calculate K, Boltzmann's constant, T is the temperature in Kelvin. 27 degrees Celsius means how many degree Kelvin? 300. And Q is charge, 1.6 into 10 is to minus 19. So write down what does this diffusivity or D means. Diffusivity is a constant. Let me write D only. This D is a constant associated with diffusion transport. Mobility constant associated with drift transport. And further, when I teach you what is random thermal motion, random motion is still remaining pending. I know that. That will immediately discuss in the next class. This Einstein relation will show that both drift and diffusion process are based on random thermal motion. Okay. Now write down two facts. Facts means this I'll again clarify them later why they are so. Fact number one. In response to electric field, in response to electric field in drift transport, in response to electric field in drift transport, we get constant velocity of carriers and not acceleration. Underline the word constant velocity. Fact number two, in diffusion transport, what do you mean by diffusion transport? Concentration gradient. Again, we get constant velocity of carriers and again not acceleration. I will tell you the reason why, but again it involves the explanation of random thermal motion. So verbally I'm telling you, I am not make you write that. So in semiconductor, as I already told you, there are other particles surrounding the electrons and the holes. Correct. So when an electron travels in a semiconductor crystal, they may encounter other particles also. So electrons travel at a particular speed. Yes or no? Velocity. Yeah. So they might hit other particles. In response to the electric field, if we increase the electric field, the electrons will try to run away even faster. That should happen ideally when assuming that no other particles other than electrons and holes are there. So there will be other particles also, photons, phonons. They might hit them, their speed reduces and attains a constant velocity. Same, if you are at 20,000 feet above the air and you are in an aeroplane and you want to, do diving. Yeah. So there, when you turn on your parachute, you are attracted towards the earth at a constant velocity. If the velocity is not constant, if you accelerate, you cannot survive because the earth is pulling you down by g. So that's why parachute, what they do, they maintain a constant velocity. Are you understanding? So this is a concept which similarly. So electrons and holes are scattered. Scattered matlab they hit and they change their direction. And this is due to random thermal motion of electrons and holes. And that we will discuss in the next class. Okay, so for today, that's it. In the next class, what we will discuss is drift and diffusion current equations. Also, we'll discuss the concept of carrier lifetime. What is the lifetime of a carrier? Because carrier also have a lifetime. It's very, very small in nanoseconds. Then we'll also discuss what do you mean by random thermal motion. So these are the last topics which we are pending from module number 1. All right. So